Welcome back to the EasySpin Academy 2020. This is day 2 and session 3. In the previous 2 sessions we looked at least squares fitting. In this session we're going to leave that topic for a moment and look at EasySpin's capabilities to simulate slow motion spectra. This is mostly relevant for nitroxide radicals in fluid solutions, but also applies to other radicals and transition metal complexes in fluid solution. EasySpin's function for slow motion spectra is called Chili. Let's start with a very simple example. Let's take a spin system with a spin 1/2. Again, you do not have to specify spin 1/2, but you can, to be explicit. If it's omitted, it's automatically assumed to be spin 1/2. Spin system that takes some G values and 2 and 2.1. And remember, if you only give 2 of the 3 G values, that's equivalent to an axial G tensor and basically means the same thing as specifying 2, 2, and 2.1. This not only saves you typing, but also allows you to keep the Gx and the Gy values locked together. If you were specifying them as 3 separate values, and if you do fitting, then you would have to vary the first and the second separately. But if you know that your spectrum is axial and that these two are identical all the times, this is a much better way of inputting it because you only have 2 parameters instead of 3. Okay, now the new parameter is the correlation time, T-core. This time tells you the time scale on which the molecule tumbles. So basically, let's actually write this down. Let's take 0.1 nanoseconds. So 0.1 times 10 to the -9 seconds. What does this mean? That's 100 picoseconds, right? It means if you have 2 nitroxide molecules in this particular sample, or it's a solution, it will take about 100 nanoseconds, 100 picoseconds before the orientations become uncorrelated. So if you take those 2 nitroxide radicals at time 0 with the same orientation and you let them just diffuse around, after 100 picoseconds, you can't tell anymore that they were started out with the same orientation 100 picoseconds ago. So that's what the rotational correlation time means. This is the rotational correlation time. All right, we need an experiment. Microwave frequency, we're going to stay at X band, and the range, field sweep range, let's say 320 to 342. And then we call chili, and chili works the same way as pepper, which is for solid state, or garlic for the very liquid fast tumbling limit. You first supply the spin system parameters and then the experiment parameters. All right, Control Enter now will give us a spectrum. Now 100 picoseconds is a fast rotational correlation time. It results in a lot of averaging of the orientations on the EPR timescale, and instead of a nice powder spectrum, you just get a single line. Now let's see what happens if you slow down the correlation. In order to do that, you can highlight the 0.1 here, then right click and click on increment value and run section, which gives you a little menu that allows you to change this value and then rerun the section. So I entered here 0.1, and if I click on the plus, it will add this number to this here and rerun the entire section. Basically, we get the spectrum for 0.2. As you can see, the spectrum got a little broader. 0.3 nanoseconds, and now just focus on the spectrum, what happens. 0.4 nanoseconds, 0.5, 0.6, 0.7, and you can see it gets very broad. This is called the slow motion regime. In this regime of motion, the spectrum consists neither of sharp lines nor of a well-defined rigid limit powder spectrum. If you slow it down further, 0.8, 0.9, 1 nanoseconds, 1.1, 1.2, just keep going a little bit. As you can see, as we approach multiple nanoseconds here, the spectrum becomes more defined. It is overall broad, but the spectral features become more defined. Let's now go in 0.5 increments. 3, 3.5, 4, 4.5, 5, 5.5, 6, 6.5, 7, 7.5, 8. Let's go in steps of 2, 10, 12. As you can see now, once we hit about 10 nanoseconds for this particular spin system, this spectrum looks pretty much like a rigid limit spectrum. So Chili is the function that allows you to simulate spectra over the entire motional range from fast to very, very slow, almost rigid. In principle, you could use it also to simulate the rigid limit spectrum, but it's much slower. So for a rigid limit, always use Pepper, which is dedicated for that. So if you want to learn about Chili, you just look about the documentation. There's two places. There is a user guide on the slow motion regime. And then there's also the Chili reference documentation for Chili the function. So now what we could do, we could actually go to a nitroxide radical. So we're going to clear. I'm going to just copy some from my prepared script here to save some typing time. We start out with defining the experiment, an expand experiment. We're going to look at the absorption spectrum, and we have a field range typical needed for a nitroxide. Then we'll take the nitroxide parameters. Again, I'm copying that. Typical values 2.008, 2.065, and 2.023. You only need to model an N14 nucleus in a nitroxide, typically for expand. And the hyperfine tensor, which 20, 100 megahertz, with the largest hyperfine coupling in the same direction as the smallest G value, which in how we set it up is the Z direction in a molecule. Okay, now let's simulate 3 spectra with 3 different correlation times. sys.tcore. Let's do one with half a nanosecond and just simulate that with Chili. And then we simulate one with 1 nanosecond. Let's call this the second spectrum here. And finally, simulate one with, let's say, 4 nanoseconds. So we're calling Chili 3 times to get back 3 separate spectra that correspond to 3 different correlation times. And now also let us simulate the rigid limit spectrum for reference. And for this, we're gonna request we have to call Pepper, and we go on a request separate transition output. And so let's call this B0 and spec 0 and call that with Pepper sys exp opt. So Pepper only simulates the rigid limit, so it will completely ignore the correlation time setting. All right, let's run all these spectra, all the simulations. It says busy here in the bottom left. I'll take a second or so. Yeah, it's done now. And now let's go plot this. So we're gonna make a few plots here. So we use the command subplot. Subplot divides our figure into separate plots. And the first 2 parameters, as we talked about yesterday, set up a 2x1 matrix of plots. So 2 rows and 1 column of plots. And we're going to go to the first plot. And there, we're going to plot all the mobile spectra. We're going to plot B1 spec 1, B2 spec 2, B3 spec 3. And then we move to the second plot on this 2x1 plot layout. So 2, 1, 2. And we're just going to plot the rigid limit. B0 spec 0. Okay, now I can run this section again. Either by pressing Control Enter or Command Enter on a Mac. I could also just click Run Section up here in the ribbon bar. Run Section, and voila, here we have the answer. So now you can see on the top, you can see the nitroxide absorption spectra, which is the integral of the CW EPR spectrum for 3 different motional regimes. And at the bottom, you see the rigid limit without any broadening. We should probably add a little bit of broadening here, just so it doesn't look so artificial. See if 0.2 millitesla is too much. No, that's more reasonable. Okay, so now you can see that the low field line is basically an averaged out position of the red rigid limit subspectrum. The middle field line in the motional spectrum is just an average of the purple middle transition here. And the high field line is an average of over these broad high field transition from the rigid limit. These three transitions correspond to the three different quantum states of the nitrogen-14 nucleus. And as you can see, the high field line is the broadest. It's the broadest and therefore also the lowest in intensity. And the reason for this is that in the rigid limit, this transition is the broadest. So it actually takes more tumbling, faster tumbling to completely average it out. The line that's easiest to average out is the middle one, and that's why the middle line is usually the sharpest. So this is valid for X band. Of course, if you go to Q band, the situation will be different because the rigid limit spectrum will look different. Okay, now let's go to do some anisotropic diffusion. So far we've assumed, we just gave one correlation time, and that assumes that the molecule can rotate around this way or this way or this way with the same speed. And that's only true, strictly true, if the molecule is spherical. But neither a nitroxide or any other molecule is exactly spherical. So what is happening is that some molecules tumble easier around one axis than on the other, especially if they're elongated. And you can take this into account in your simulation by providing different correlation times for the different axes. And here's an example. Again, let's start out with an absorption spectrum at 9.5 gigahertz. Let's define a system, just a very simple spin 1/2 system with G values 2 and 2.2 and a little bit of convolutional broadening of 0.5 millitesla. And now let's set the correlation time anisotropic, 30 and 0.1 times 10 to the negative 9. What does this mean? Again, this is seconds. It means it relates to the G tensor and to the molecular frame again. The axial G tensor, if you recall, the first number gives both the X and the Y value for G, and the second number is the Z value. The same for the correlation time. The first number is the X and the Y value, and the third one is the Z value. Now what does it mean? The Z value means how fast the molecule can tumble around its Z axis. Right? And I set this to a very small number, so it means it actually tumbles very easily. And the 30 nanoseconds is very slow, so tumbling around the x-axis or the y-axis is harder. And this kind of indicates elongated molecules. For example, just like a pen, right? A pen can tumble really easy around the z-axis, but much harder around the x or the y-axis. Okay, let's calculate now both the rigid limit spectrum and yet simulate the motional spectrum with this anisotropic rotational diffusion. Let's also maybe just scale the spectra to the maximum of each other so they're more comparable shape-wise. And finally, let's just plot them, B0 spec 0 and B comma spec 0. So here what I'm doing is I'm dividing each spectrum by its maximum. So after scaling, they both will have the same maximum of equal to 1. And then I can plot them by just plotting the first and then comma and plot the second. And always give the x and the y coordinates. All right, so we should probably clear the figure here as well. I have a typo here. And there we go. Okay, now what you can see. There's very little motional averaging visible. We can see some wiggles here. These wiggles are simulation wiggles. We talk about them in a little bit. But why is that, right? If the molecule tumbles around the z-axis, it's just swapping the x and the y values all the time. The z is staying the same. But x and y in this molecule are the same. The g values are too. But what now if we change it the other way? We're going to let it not tumble around the z-axis, but tumble quickly around the x and the y-axis. If you tumble around the x and the y-axis, you're going to swap the z value with the x value. And then we should see a huge effect. And voila, you see a lot of averaging. So this is how anisotropic diffusion works. Now we need to go back and think about what is going on in this case, where we see the simulation wiggles. And so Chili is actually a fairly complicated theory, and implements a so-called stochastic Liouville equation, a solver that's based on an eigenfunction expansion approach developed by Jack Fried at Cornell University. And similar as in Pepper, where you have to specify the number of orientations to get good orientational averaging, you do need orientational averaging here as well, except that the option is slightly different. It's called opt. Where are we here? Here we are. It's called opt.llmk. And we're going to make a simple example here. I think we can just start from this. We can just delete the rigid limit spectrum because we don't need that. Just to simplify what we're doing. So again, see, we have the experiment definition, the spin system definition. Let's add some options now. And this takes 4 numbers. 2, 0, 0, 0. We can start out with very low values for these numbers. These need to be integers. And they completely specify the basis that is used to represent the spectrum. And the higher these integer numbers are, the larger the basis and the better the representation. If we start out with 2, 0, 0, 0, it's exactly what we have here. And now we can increment this, maybe to 4. Oh, it doesn't work because I have to include opt. So let's go back to 2, 0, 0. Typical mistake here, you specify options, but you forget to tell Chili about those options. Even I run into this problem a lot, despite many years of experience with EasySpin. So watch out. I haven't found a good way around this yet to avoid this type of mistake. Okay. So you see, this is complete nonsense. The basis is way too small. It looks very different from the previous spectrum. Now if we increase this to 4, it looks better. I'm going to, again, use the right-click increment value and go up by numbers of 4. 6, 8, look at the spectrum. 10, 12, 14, 16, 18, 20, 22. Well, it looks like it didn't change much anymore from 20 to 22. Okay, so let's go back to 20 and start incrementing the second number. The second number usually should be odd, so we start with 1. And we're going to increment by 2. 3, 5, makes no difference, because you can probably leave this at 0. Third number, 2 makes a little bit of a difference, okay. 4 doesn't change anymore, and so on. So this way, by manually increasing each of those numbers, you'll get you have a handle on getting a smooth spectrum. And you should always, when you do Chili simulations, adjust this basis size to give you a smooth converged spectrum. So increase each value of those 4s in turn until you get to a situation where no increase will change your spectrum at all anymore. And it takes a little bit of iteration, and it's manual. And it will also depend on your spin system parameters. So watch out. If these values are too small, Chili will give you an unconverged spectrum, and your fit will not be correct. Sometimes it's hard to tell whether the spectrum is not converged just by looking at it. You always have to fiddle with the basis and increase it until you see no further changes. Okay, another thing to briefly mention, let's see what the time is. 9:20, okay. You have 11 minutes in this section. Let's talk about partial ordering. So one big application case for nitroxide spin labels and slow motion simulations is to model nitroxides attached to proteins. And if a nitroxide is attached to a protein, it will still have its intrinsic mobility due to its size and shape, but this motion will be restrained and hindered by the surrounding protein environment. In fact, it can be hindered so much that some orientations are completely inaccessible for the nitroxide because it just might clash with other side chains of the protein. We can take this into account in Chili with a concept called partial ordering, which basically tells EasySpin to exclude or make certain orientations of the nitroxide much less likely than others. And here's how it goes. First, I'm gonna just again copy up from my prepared script a simulation for a spin nitroxide, here with the G value, the nitrogen and the hyperfan value, and the correlation time of 1 nanosecond. So now in order to specify some motional restrictions or hindered orientations, you have to specify sys.potential. And it's named potential because it describes a sort of an energy landscape as a function of orientation. It will tell, so certain orientations will have a low energy and other orientations of the nitroxide will have a high energy. And then those high energy orientations will be less accessible than the low energy orientations. I don't have too much time to go into the detail, but it uses a Wigner function expansion of an orientation potential here. And we can make a very simple one. We need 3 numbers to specify the shape of the function we want to add, and 1 number to specify how intense it is. We can look at this before we do any plot. So remember, this is new in EasySpin 6.0. We can actually look at this orientational potential with a function called Ori Potential Plot. And what you have to provide there is just this actual potential. And this is also new in EasySpin 6.0. Let's see how it looks like. And there we go. We get a figure that shows us a sphere corresponding to the various orientations of the nitroxide, and with a color bar that gives us the population density. And actually this label is incorrect. Let's switch over to the actual population density. So this shows us the equilibrium population in colored form. We can rotate this as well. You can see it's very dark on the north pole on the plus and the minus z axis, and it's gray in the equator, meaning that the nitroxide is more likely to be found along these axes than along the equator. So it's like more up or down and not as much sideways. We can increase the potential energy, let's say, to 2, and again plot this and look at the populations. And now you see the difference is much starker. It's dark where there's a lot of nitroxides, and it's light around the equator where there's fewer nitroxides. And you can also, this is just the populations, but you also can look at the energies. Blue indicates low energy, and yellow indicates high energy. So this is a function that allows you to actually look at what sort of orientational distribution you are inputting into the simulation. And a reminder, this is new in EasySpin 6.0. It's not available in EasySpin 5.2. Okay, so let's put in a microwave frequency. And now this nitroxide is assumed attached to a protein. And just to make the simulation fast, we're going to assume this protein as a single orientation. So it's in an aligned film or aligned bicelles, or maybe even in a protein crystal. So we say crystal orientation equals, let's say, 0, 0, 0. Now we're gonna run this, and I think a good basis, we have to specify a good basis for this, and I tried this out before, and 6022 is pretty good. And I'll just run chili sys, exp, opt. And if you run this, we get a spectrum that now includes the partial ordering. You see, you don't see much here. There's not a lot of structure, but if I remove this potential and set it to 0, you see there's a spectral difference. You see the splitting between those lines is much narrower. Actually, can I say that? No, I can't say that. Let's put in the actual range. 330, 345, 348. Okay, so this is without potential, and then with axial orientation, with potential. In fact, the splitting is a little larger, even though the intensities of the lines haven't changed much. So that is an indication that you have some orientational ordering or partial ordering going on, and sys.potential is the way to include this into your simulation. And of course, you can also fit these numbers. You can fit the strength of these orientations using ESFit. That's partial ordering. The last thing, it's 9:15. We've got another few minutes. The last thing I would like to show you is how you can compare chili and garlic. So chili is provides a very general algorithm that works for the slow motion regime and the fast motion regime, and also the isotropic limit. So where the molecule is tumbling so fast that all these anisotropies are averaged out. Garlic, on the other hand, only works in the isotropic limit, but it also has capabilities for the fast motion range, which is shown right now here in the spectrum, where a spectrum consists of separate, distinct lines that they look pretty Lorentzian, but they might have different line widths. If you're in this regime, this is called the fast motion regime. So you're moving fast relative to the spectral anisotropy, but not fast enough to completely average out everything. So we can again start with a nitroxide. I'm just going to copy my nitroxide definition. It's kind of always the same, right? The G values, the nukes, and A. A correlation time, I'm entering 300 picoseconds. So that is more typical for a nitroxide by itself without a protein in a normal aqueous solution, and some additional Lorentzian broadening. And I'm going to use microwave frequency of 9.5, and you can use garlic now to run this experiment. And what you see, we get a nicely motional EPR spectrum where the third line again is a little broader and less intense than the other three. We can compare this between garlic and chili with the same input parameters. Let's call this B1 and B2, spec 1 and spec 2. Probably would be good to specify the range manually. 335 and 342 are good range limits. And plot B1 spec 1, B2 spec 2. And you see they're completely coinciding. And that's another feature of EasySpin, is that these different simulation functions, although they are based on very different algorithms, their intensities are calibrated, right? You can compare a chili spectrum to a garlic spectrum in terms of intensities. They always refer to the same number of spins. Okay, now if we slow down the motion, we go to half a nanosecond, 0.8 nanoseconds, 1 nanosecond. Oh, I have to use chili here. Let me go back. There we go. Okay, that looks better now. Chili and garlic are almost coinciding. Okay, and if I increase that now, if I make the motion slower, you see that they're starting to get out of sync. The blue one is the garlic simulation. The red is the chili simulation. The chili simulation is always better than the garlic simulation, but you can see you can almost go up to 1 nanosecond, and garlic gives you kind of no right representation. And this is useful if you have this type of regime, because garlic is much faster than chili. However, it does not include any orientational partial ordering effects. So this concludes a brief overview of the slow motion simulation capabilities of EasySpin, which are provided by the function chili. I've only shown you nitroxides and simple spin 1/2 systems, but chili can handle high spin systems as well, and it's way more general than what I've shown here. But as usual, you can find more details in the documentation and also in the examples. With this, we are at the end of the slow motion session. We'll have an 11-minute break, and after that we reconvene for a session on rapid scan CW EPR. See you then.